We've discussed how an electric field originates from a single charge. We are now ready to talk about the situation where multiple charges, because frankly, nature is rarely ever that simple that you only have to deal with one charge. Basically, since the electric field of a single charge is a vector, which means it has a magnitude and a direction like so, the electric field of multiple charges may be calculated by adding point by point their individual electric fields. So let's say at this point we have an electric field vector due to one charge. We have one due to another charge in that direction. You would just add these two vectors and get a vector in this direction. Now, for this course, we're just worried about fields in one direction. So it would be more like an electric field going this way. Then it's being supported by another charge with the electric field going this way. So the total electric field would just be the length of this vector in this direction. We'll cover this in more detail later on in the section entitled The Net Electric Field. Remember, electric field lines do not really exist. They're a mathematical way of showing the strength of an electric field and which way it's going. So the first rule we're going to use, electric field lines always start on a positive charge and terminate on a negative charge. If you're only dealing with one charge, this termination point would be at infinity. The electric field line would keep on going until it reaches infinity. The density of the magnetic field line's distribution is proportional to the size of the charges. So if I have a real large charge here, we will draw a lot of electric field lines from it, and this would continue around the whole side. If we had a smaller charge, we'll just draw a smaller charge, maybe we'd only draw a couple electric field lines. That shows that this charge here is much greater than this charge. Now, the lines never cross. Notice how all these lines are separate. If they were to cross, let's say I'll draw a positive charge here, I have one line going this way and another line doing this. The problem is right at this point here, because recall the electric field lines tell you which way the force would be on a positive test charge. So if these two lines cross and I put a positive test charge here, which way is the force? Is it this way? Is it that way? Well, clearly it can't be both, so we prohibit that by not letting these field lines cross. And the lines are continuous. That just means there's no breaks in them. For example, a field line doesn't go like this and then pick up over here. It's one continuous line. First, consider the electric field due to two charges, and we'll make them both the same. This one here, you have two positive charges. Here you have two negative. Notice one thing first. Right in the middle, there is no electric field. Why? Well, let's look at what this charge would do to a positive test charge. It would have an electric field pointing in that direction. This charge would have an electric field pointing exactly opposite and exactly the same length. So these two would cancel out and you have zero electric field. Notice that goes right up all of these points. There is no electric field. So if you were to put a positive charge there, nothing would happen. It would just sit there. Same thing for two negative charges, and notice the difference here. With the positive charges, the arrows point away. With the negative charge, the arrows point towards it. So the configuration is exactly the same, it's just that the arrows point in different directions. Again, we have two charges, but in this case they are unlike charges. They are different. You have a positive charge and a negative charge. There is no place where the electric field is zero. The electric field has a value everywhere. Because if we go right back here in the center again, the positive charge would be pushing this test charge this way to the right. The negative charge would be attracting it this way to the right. So when you add those two together, you have an electric field going to the right. Notice how the lines start on the positive charge and come to the negative. And this is just a limitation of our paper. For example, this field line would probably go something like this, connect up there. And now this field line on this side will probably, depending on the size of the charges, just keep going way out until infinity, or until it hits another charge. This is a very famous configuration. This is called the electric dipole. You may remember that the water molecule from chemistry, shaped like this, oxygen, you have a hydrogen over here, a hydrogen over here. The oxygen tends to attract the hydrogen's electrons. It's a covalent bond, but they stay more on this side. So you tend to have a negative charge here and a positive charge here. So that's a practical application of the electric dipole that we're talking about here.